So guys, welcome back to this particular video. In this video, we will be mostly looking at a lot of PYQ questions, as well as the goal of this video is not just to give you the answers. Also, I want to cover some of the important concepts that goes into solving these questions. So with this, let's start today's session. So guys, the first question that we are going to see is about max apps scalar, and in this particular question you have been given a data set. Say A, you have to initialize the max apps scalar, then you have to create a scaled version of that using the fit underscore transform A, and then we have to print the minimum value of this scaled minimum. So there are two ways to solve this particular question. Either you can focus on the theory that goes into this, or you can just apply the formula and get the result. This is the fastest way. This is little bit slower. Anyways, so the theory is max apps scalar. Scale your data within 1 and -1. So maximum will be your 1 and minimum will be your -1. Okay, so with this, minimum is -1, as you can see, right? This is your answer. On the other hand, for the formula, it is very simple. You have to do x by max of absolute value of x, and this xi means that is the current value of x. So -3 is the current value and max of all these x is 4, right? Because it is -4. So if we have an absolute value of -4, it will turn out to be -3 by 4. So whatever value goes, it will be within 1 to -1 range, right? So let's say for -4, if we see here, so -4 divided by absolute value of 4. Right. So this is the base idea for solving this particular question. I hope that you understood this. Okay, now let's move on to our next question. So our next question is, given below a white train list which consists of a coffee order preference by a customer in a cafe. So this is your white train and you have to use multi-label binarizer from Scikit-learn to convert your white train into numbers. So which of the following option matches the output of the following code? So you have this particular code. Let's see what this code does. So it imports the multi-label binarizer. Okay. And then it defines the classes. So based on these classes, you have to follow the white train. So these are labels that are given to you, right? So this will be 1, 2, 3, 4, right? So if you see here, this 1, 2, 3, 4 are indices of whatever label vector array you will be creating using this fit underscore transform white train. So in this particular case, you have to check which particular position has this, and then you have to solve this. Wherever there will be a cold, we will set it at 1. Wherever there is large, then also we will set it at 1. Rest all will be 0. So every time we will be using this, we will be actually creating it like this: cold, hot, large, small. So this is just a list of arrays. So that's why I'm just expanding it to help you understand, nothing else. So here cold is 1, right? So cold will be 1. Also our large is present, so here large will be present, 0, 0. Next, small is present and cold is present. So cold again is this, small again is this, and rest 2 will be 0. Third one, small and hot. So small this, hot this, and these are 2, right? And finally large and hot. So large this, hot this, and these are zeros. So whichever option matches this, it will be the output. And for this particular question, option A matches this, right? So that's why we are using this particular as our answer, and this is the way how you have to solve. Okay, now moving on to our third question. So our third question uses min-max scalar, one hot encoder, column transformer, and then we have to create our numpy array here. So these are numbers, say it is x1 and this is our feature x2. Then we are creating a pipeline using column transformer, and we are setting 2 values. So if you see here, this is num, this is cat. So that means numeric pipeline and categorical pipeline. So in numeric pipeline, you are using min-max scalar, which will set the value of which particular column we have to use. So it is 0. That means we have to use this particular column as our min-max. Okay, and then we have to one hot encode also for our next column, right? So next column will be this, will be one hot encoding. I will use OHE. Okay, now the main thing that you have to see here is what is the output that they are. So they are transforming the data using fit underscore transform, and then they are printing the data. So here x underscore transform 0. So 0 means first row. What will the first row? So based on this, you have to apply min-max scalar on this first value and one hot encoder on this first value. So there are many ways to solve this particular thing, but you can go option wise here. So for one hot encoder, if we see, which is based on this, and these are all independent, so that means that wherever there is a apple for our first case, right? So then it will be like that. And one hot encoder, by the way, works on the dictionary format, or what you call as alphabetical order. Okay, if nothing is specified, if they are default, right? So apple will be given 1, banana will be given 2, and cherry will be given 3. Okay, and in this particular thing, if you see here, you have apple, banana, apple and cherry. So since we are focusing on just this particular row, our output for this particular setting will be 1 0 0. Why 0? Because we don't have banana, although we have apple, but it is, since it is unique, already defined, so we will not take it, and cherry will be 0. So here let's see which all option matches that. So 1 0 0 1 0 0. These two options fail, right? So we can't use those for our one hot encoding. Now the main question is, will be this 0.25 or 0? So next is min-max scalar. So min-max scalar is x minus x min by x max minus x min. So based on this, if we try to convert 2 minus what is the minimum value, 1, divided by what is the maximum value, 5, what is the minimum value, again 1. So this will be 1 by 4, that's 0.25, right? So 0.25. So this is our answer. Now let's move on to our next question, and for this one I will be skipping this particular thing because I also have some doubts in this. Once I will clarify, then I will share it with you. Next is question number 5, and in this question you are asked that from sklearn.processing import label encoder, you have cat, dog, fish, cat, bird, dog, bird, and then you are using label encoder and encoded data encoder.feed underscore transform data. So it is asking, if we print our encoded data, what it will contain first of all, and which all the statements are given here are right. Okay, so label encoder again works on alphabetical order if nothing is specified. So in this particular case, our bird will be given a value of 0, our cat will be given value of 1, dog will be given a value of 2, and fish will be given a value of 3. Okay, so it says encode data will contain only value 0, 1, 2, 3. So that's true, because label encoder encodes that value into numbers, and we get that encoded numbers as that. So basically your output will be like, it is 1, then 2, then 3, then 1, then 0, then 2, and then again 0. So this will be type of output that you will be getting. Okay, so that's first one is right. If elephant is passed to encoder.transform, it will successfully transform to an integer. No, it will not, because label encoder always learns the data and then transform it. So since our data don't have elephant, it will not know anything, and it might throw an error. Label encoder assigns higher integer value to more frequently occurring labels. No, that's not true. It mostly uses the alphabetical order. And finally, after calling encoder.inverse transform to, it will be returned to dog. So encoder encodes your data, and inverse transform is a method that can be used to convert the label back to your actual value which was present in your data, and it requires you to pass in the index or the integer that is given to it. So since our integer 2 is associated with our dog, that's why it will return a dog. So this is the whole idea of how things work, and if you want, let's just clarify things. So encoder dot transform, what it does. So encoder transform methodically is typically used in machine learning and data processing to transform data into formats suitable for training and prediction. Okay, and here you can see this. And now if we do encoder dot inverse transform, let's see what it gives. The inverse transform is used to reverse the transformation applied by transformation method. It converts the encoded data back into its original form. This is particularly useful when you want to interpret results of a machine learning model in terms of original data. And here is how we do it. So encoder.inverse transform encoded data converts the numerical label back to original animal names for this particular case. Okay, so this is how you can do it. Now let's move on to our question number 6. The question number 6 is pretty simple. It says that what is the main principle behind your dummy regressor prediction strategy. So the dummy regressor, as the name suggests, it's a dummy, and it tries to predict based on mean, median of a target variable. This is just directly from theory for all the instances. So say if I have a data where my class 0 is 650 and my class 1 is just 250. So my dummy regressor will actually predict all the classes as 650. Okay, or maybe taking the mean or maybe something like that. Basically it is based on the strategy where defined in the constructor. Okay, it's the main idea. So predict the mean or median of the target label for the instance. So mean basically refers to average and median basically refers to the middle value of that. Obviously it is also allowed for our most frequent. So mean, median, most frequent. All these strategies are possible with dummy regressor. Fit a complex mathematical function of dummy data wrong. Randomly shuffle the target level value to make prediction wrong. Predict the sum of the input feature for the instance wrong. Okay, so this was the main idea behind it. Next question is very important and I have seen it repeated many times. So this is a very important one. Which of the following scenario demonstrate high level of empirical error but potentially good generalization? So what it asks is that you have a model on which your train data and validation data should be such that when you input your test data, it would generalize well. So it should not overdo your training data and your validation data. So there are lot of options given there. Let's see. A model for that fits the training data perfectly and performs well on validation data. If it does well on validation data, then there is no high level of empirical error. So that's totally wrong. A model that performs equally well on training and validation data, if it is already performing well on training and validation data, then no empirical error again, because error will occur if it is not performing that, right? So a model that has low training error means like they have low training error but slightly worse performance on validation data. So what is happening here is that your training data has very low error, but when you do for your validation data goes a little bit up compared to your training data. So it is normal that your validation data might have large error compared to your training data, but it will not perform that very bad when it comes to generalization on your test data. So that's very important to understand. And now the model that consistently underperforms on both training and validation data, then we don't have a good generalization in this case, right? Because it is performing bad on validation data also. So that's wrong. Now let's move on to question number 8. In this particular question, it says you have this particular code, you have this particular data, you have to apply standard scalar. What will be the original data and what will be your scale data? So it simply asks what does this above code achieves. It doesn't ask you to what will be the output of this, right? So converts the numerical value in the data array to categorical labels. No, that's not the thing. Standard scalar basically scales your data. So if you have data at different ranges, say one particular feature in the range of 10 to 100, feature 2 in the range of 1000 to 8000. So in this case, model will try to prefer this particular thing more because it has more values, right? So the weights that will be assigned to this will be more. So to handle those things that model gives equal chance to everyone, we use standard scalar x minus mu by sigma, where mu is your mean and sigma is your standard deviation. And what it does, it just brings your data within the mu as 0, that is mean as 0, and sigma as 1. So this is the right thing. It applies logarithmic transformation to the values in data array. Wrong, because it is just simply scaling, nothing else. It removes the mean and scales the feature in the data array to a specific range. So that's wrong. Standard scalar, you don't have any specific range. It can go negative, it can go positive, but it can go to any value. It doesn't matter. Minimum and maximum is not like limited to -1 or 0 to 1. Okay, so that's question number 8 completed. Now let's move on to our next question. This again I have seen repeated few times. So here you have been given a data, very simple one, and then you are set to add a polynomial feature to it, and the polynomial feature has this degree of 3, okay, and interaction only is 2. So due to this, your feature size will reduce because now you will not have power term. So you can only have like x1 into x2 or x2 into x3 or something like that. You will not have like x1 square x2. So that will not be there for degree 3. Okay, so keep that in mind. Now we have to just check the shape. If our output shape is matching, then it's totally fine. So in this particular case, you can see that we have 3 degree, right? So what are the possible values that our polynomial feature can take? It can take x1, it can take x2, it can take x1, x2, it can take x1, x2, x3. So 4 terms, right? So how many have this 4 terms? So first one has this 5 term, 1, 2, 3, 4, 5. So this is wrong. Again, this is very large. This could be true if interaction only would be false, right? Again, this is wrong. So this is the answer for this. One thing to note that when you will calculate, it might be that this particular value may not come. But the whole idea for this particular question is that you should understand how many terms will be created. So you don't have to actually calculate those values. Keep that in mind, okay? So with this, we have come to end of question number 9, and question number 10, we will look into that later. Now moving to our question number 11. So our next question is, using the confusion matrix below, what is the precision score for label of class 1? So you have this 3 by 3 grid, that means you have 3 classes and you have to find the precision. Now in 2 by 2 it is very simple, but in 3 by 3 you have to convert this to 2 into 2 label matrix, right? You can do not 1, 1, not 1 and 1. So this will be your confusion matrix. You can also relate it to 0 and 1. No issue with that. And then you have to calculate. So it says not 1 and not 1. So that means that all these diagonals, right? Because we have 2 and it is not predicting as 1. So 2, then we have 2, it is predicting at 2. So that's totally fine, no problem with that. After that, we have 0 and it is not predicting as 1. That's 3. And after that, we have 0 and it is not predicting as 1. So 1. So these all values are important ones. So 2, 2, 4, 4, 3, 7, 1, 8. Next is, you have not 1 but predicted as 1. So those are these values, right? 0 but predicted as 1. So these are not 1 but they are predicted as 1. So 2, and these again this is 2 and this is predicted as 1. So it is not 1 and it is predicted as 1. So 4 plus 2 is 6, right? So these 2 are 6s. Next is 1 and not 1. So 1 and not 1 means actual is 1 and it is predicted as not 1. So 1 is this was actually 1 but it was predicted as not 1. So this was 3, and also it is 1 but it is predicted as not 1. So that's 2. So that means 1. So this is 4, and finally 1 and 1. So it is predicted as 1 also and it is actually 1 also. So that's 2. Now based on this, we have to calculate the precision score. So precision is equal to TP by TP plus FP, right? So what will be our here? So 2 will be 2 and TP will be, it is true positive, again 2, and what will be our false positive? So this is false positive. So 2 by 8, that 1 by 4. So 0.25 is the answer. I hope that that's pretty clear, but the main idea here is that you have to convert this 3D matrix to 2D matrix. So keep that in mind while solving this one. Okay. Next is question number 12. And question number 12 is again pretty important. I have seen it 3 to 4 times while solving my paper. So keep that in mind that this might come. In this particular question, you have been given a logistic regression and your model has this class weight of balanced and C as 0.5. Okay. And it is saying that you have to fit your X and Y. So X and Y you don't have to worry about. And it says that which of the following statement is true. So logistic regression model will give equal importance to both classes in an imbalanced data set. That's totally wrong. It will not. And the reason is because it has been set to balanced. Obviously, it would say that it is balanced, so that means it will give equal importance, but that's not the case. So this 350 is 0 and this 650 is 1. So in this particular case, what will happen is that it will take 1 by 350 and it will take 1 by 650. Whichever has higher decimal values or higher values as returned or proportion, that will be given more importance. So this is what class weight is equal to balanced means, and C is equal to 0.5 means regularization will be applied. So model does not use any regression, so that's totally wrong. The model will perform equally well on both imbalanced and balanced data set due to class or parameter. That's totally wrong. I already explained you this, right? And value of C indicates that model will apply regression. So that's totally fine as I explained, right? So this question number 12 is done. Question number 13. After training a logistic regression model from sklearn.linear model on dataset, which of the following attribute gives the coefficient of feature in decision function? So logistic regression doesn't directly output the values. It outputs a probability, right? We all know this. And then it is passed to some function, basically 1 by 1 plus e to the negative w transpose x or e to the negative z. This is sigmoid function and it outputs a single value as our max probability, right? So this is what we do. So here it says that we have to just find this, not this. Okay, so based on this we will just see. So it says attributes give the coefficient feature in decision function. So the keyword is coefficient. If you see the coefficient of features, that means that it will be model dot coef underscore, and this will be only used after training. So coef underscore will give you an array of values where each value will represent a particular observation, prediction. Okay, model dot params will give you the parameter, so this wrong. Model dot intercept will give you this the intercept value of w1 x1 plus w2 x2 plus w3 x3 up to so on plus w0. So this w0 will be returned for this, and model dot feature weights will just give you the weight of the feature that is given to it, but it is not always going to work here. Okay, so just to clarify here, if we do model dot coef for logistic regression, let's see what the output is. So in logistic regression, one attribute contains the coefficient weights of the feature used in the model. These coefficient represents the relationship between each feature and log of odds of target variable. So this is how you will implement that in code, and it will return an array of coefficient for each feature. If you have multiple classes, then coef will be a 2D array where each row represents to the coefficient of one class. So that's the main idea that I wanted to share here. So that's for this particular question. Next question is question number 15. So here if you see, you have your array, you have also your label array and the feature array. Then you have your classifier as Gaussian naive Bayes, and you have to fit your x and y. The new data is np.array this. So new data is basically for prediction. Okay, and predicted probability will be classifier dot predicted proba underscore new data. So in classifier you have a predict function and you have a predict proba function. In predict proba you will get a range of probabilities, those raw things that I showed you earlier, right? And in predict function you will just get the output of the prediction, say it is class 0 or 1, but here you will get all the probabilities and get a single value when you will pass it to a sum function which will give you the actual predict value. Okay, so keep that in mind. And in context of above code, what information does array predict proba contains? The predict classes for new data points? No, this is for predict function. This is boundary of values for the classes? No, Gaussian naive Bayes will not do that. It is just simple probability based algorithm. The posterior probability of classes of new data points, yes. So posterior probabilities it says, right? So that means multiple probabilities, and it will just return an array where after applying Gaussian naive Bayes, you will have a posterior probability. Posterior probability will just be found using Bayes theorem in general. Earlier you already had some probability of something occurring, but after seeing the proof you are again using it for your Bayes. Okay, likelihood estimates of the new data points, so that's totally wrong. And now let's check whether we are right or wrong. So if I do Gaussian naive Bayes posterior probability Scikit-learn, let's see what we get. You can see that it simply says predict proba method contain class obtain the posterior probability for each class, and it will return an array where each row correspond to the posterior probability of the classes for each of the sample, like I have shown you earlier. Okay, so this is the base idea here. With this, we have completed our question number 50. Question number 16, and here you are saying you are working on a binary classification problem where data set is relatively small, okay, and you suspect that linear decision boundary will work well due to distinct class separation. So that means it is a linearly separable data set. That means you can fit a decision boundary so that both the classes are mostly separated. Okay, additionally, you want to perform logistic regression with L1 regularization for improved feature selection. Which solver most appropriate for this scenario? So the answer is liblinear, and the reason is, first of all, liblinear can handle small as well as large data set. So small data set it can handle. Second, it is good for linear kind of relationship. Third, it can handle L1 regularization pretty well. Obviously, I'm not very sure with this particular options. So let's check what are each of these do and how they relate. Okay, so for this I will use Newton's CG, SGD, LBFGS, liblinear. Okay, and we will just check the differences because that will help us understand where to use what. So Newton CG says supports L2 regularization only, and we are saying that we have to use L1 regularization. So Newton CG fails. Stochastic effort or optimization suitable large scale data set, so that totally passes, and it is efficient for large data set also, and we have a very small data set, right? So that means that SGD fails. Supports L1 L2 regularization, efficient for a small medium sized data set, and it says small data sets. Okay. So liblinear handles all these things, right? LBFGS, let's see. Small medium traces L2 regularization, and we are saying we are using L1 regulation. So that's why it is wrong. Now moving to our last question of today's session. Question number 17, and it simply says what will be the output of the following code. sklearn.neighbors import k neighbors classifier 2, 3, 5, 6, 10, 11, 15, 16, 20, 21. Y is 0, 1, 1, 2. K neighbors classifier, n neighbor will be 3. Matrix is Euclidean, weight is uniform, and you have to fit this, and you have to predict 8 and 9. So there are many ways to do this. One way is very simple, just check the majority count of the classes within that particular range and output that. And here you can see that it is 1, 1 and 2. So that means that for 5, 6, 10, 11 and 15 we have 1, and 8, 9 falls within that. So we can directly do that. Or another way is to plot, because sometimes there might be a tie. So in that particular case, it is very good if you plot it. And what you have to do is you have to create this particular plot here, 2, 3, right? So 2, let's say 3 is here, 5, 6. So 5, 6 is here, 10, 11, 10, 11 is here, 15, 16, 15, 16 is here. Obviously my graph is not at the scale, pardon me for that, and 16, right? And let's add those labels. So this is class 0, this is class 1, this is class 1, this is class 1. Obviously there is one more, but we are excluding that. Now it says 8 and 9. So obviously 8 and 9 will come somewhere here, right? 8 and 9. So you can see that if we are saying n is equal to 3, that means that we have to take 3 closest neighbors, right? So one neighbor is this, one neighbor is this, and obviously this and this might have issue, right? So this will be more closer compared to this, because this has 2, 3, and this has 15 and 16, and we are close to 8. So 8 is very close to 15 compared to 2, right? So that is the main analogy. But obviously you have to calculate the distance if certain ties occur. If you have this as Manhattan distance, okay? Keep that in mind. So guys, with this we have come to end of today's session. In next session we will continue our remaining questions. Okay, so I hope you learned a lot and you understand what are the basic things that are required to solve these questions, and I highly suggest that please practice this and understand the theory in the same way that I showed you in this particular video. Okay, so with this I will meet you in another video. Till then, bye bye.